Alright, so today we're going to be looking at objects on an inclined plane. So first we'll just take a look at an object of mass m resting on top of a surface. So the only forces currently acting on the object are the force of gravity, which is pointing straight downward, and then the normal force, which is the book pushing back up on the object with an equal and opposite force, which prevents it from just falling through the table. And that's called the normal force. So when you put the object on an incline, there are now a couple more forces acting on the object. The force of gravity still points directly downward. But because of the incline of the plane, there's a force parallel acting on the object which causes it to slide down the plane. And this is the sine of the angle between the plane and the ground times the force of gravity acting on the object. So the force parallel, which is what causes the object to slide on the surface, is equal to mg sine of theta. Pause. So the other component of gravity is trying to push the object on an angle through the inclined plane. And obviously, this object resists this force and pushes against it with an equal and opposite force, which prevents it from falling through the surface of the book. So this is the normal force, but now instead of the normal force being equal to, right now, the normal force is equal to the mass of the object times the acceleration due to gravity. And on incline, the normal force is equal to the mass of the object times the acceleration due to gravity times the cosine of the angle between the plane and the ground. Force of gravity pushes directly down, but due to the inclined plane, this is translated into the force parallel, which points down parallel to the inclined plane, which causes it to slide down, and then that's equal to the mass times the gravity times the sine of theta. And then there's the force of gravity also pushes against the inclined plane with a force of mass times gravity times the cosine of theta, the angle between the inclined plane and the surface, and that's resisted by the normal force, which is equal and opposite. So the normal force is also equal to mass times gravity times cosine of theta. So these are all our forces so far. However, once the object starts sliding down the hill, it is resisted by another external force, which is the force of friction. So the force of friction equals the normal force times the coefficient of friction, which is represented by mu. Now, when the object is not moving, this is a coefficient of static friction. Right now, the coefficient of static friction, or right now the frictional force is greater than the force parallel. But when the theta becomes high enough, the force parallel becomes greater than the force of static friction, and the object slides down the hill. So the motion of the object is resisted by the frictional force, which is mass times gravity times cosine of theta times the coefficient of friction. So at low enough thetas, the force of friction will be great enough that the force parallel isn't enough to cause the object to slide down the hill. And as the angle with the inclined plane is increased, eventually the object will start sliding down the hill. So what we're going to do now is calculate the minimum theta to cause an object of mass m with a coefficient of friction of mu to start sliding down the hill at constant velocity. So at constant velocity, the total forces acting on the object will be equal to 0. So mg sine theta, the force parallel, minus the resistive force, which is the force of friction, mu mg cosine theta, will be equal to 0. So we can factor out mg's, and because it's equal to 0, we can divide those over and they'll cancel. So if we add over mu cosine theta, we get that sine of theta equals mu cosine of theta. So mu equals sine over cosine, and sine over cosine equals tangent. So the tangent of the angle from the inclined plane to the surface of the ground is equal to mu. So the minimum theta that would be required to cause the object to begin sliding down the hill would be equal to the inverse tangent of the coefficient of friction.